Morning to all dignitaries, guests, delegates, faculty, researchers, and the participants from all corners of the world with great joy and immense exultation. I feel privileged to welcome and extend my warm welcome to all present here for the 5th International Conference on Smart DSC 2022. Today, we are lined up with some very interesting keynotes and paper presentations.
I welcome all the eminent speakers and guests from all over the world, from different walks of life. We feel privileged that you have come here to share your knowledge and vast experience with the student community.
We are pleased to have Dr. Kuder Altangral, Mongolian University of Science and Technology, Mongolia. I request you to deliver your keynote on bio-inspired computing, sir.
Thank you. I should share my thing. Okay. Um. Oh. Ah.
Professor, your screen is visible. You are audible
Oh.
also.
Yeah. Thank you. Good morning, everyone. I want to talk about my research, our team's research about bio-inspired computing. Hmm. Uh, Maybe I should go to full screen mode. Uh-huh. Oh, that's nice. So, oh, it's moving also. So I want thank you, the organizers, for having me today for presentation. So yeah, I will talk about uh, using that content. I think this is not so important. So, the bio-inspired computing is how we understand it's uh, like using some principles from biological processes or living phenomena. So here you can see the neural network image, and now everyone talking about deep learning and machine learning, but this idea was uh, taken from the biology, actually from the working principle of brain cell, neural cell. So, yeah, this is one of the examples. So, uh, you can see the definition also, not definition, the Professor Chiao told in 2018 that the bio-inspired computing is a field of study that uses some ideas taken from the biology, such as evolution, cells, tissues, and yeah, other things. So the second image shows that the image of some abstract image of molecular computer. So I think I will talk about this topic the the rest of my presentation because our team had some papers about molecular computing. Oh, this third image is not actually associated with computing, but uh, I put it here to show that the not only computing, but the architecture, I mean the building construction science is uh, also they took some idea from biology because you know that the Eiffel Tower is built using principles of bone structure. So not only computing, but the other sciences can take from biology many ideas. Next slide. Um, okay. So we can see this our answer. So we these ideas taken from biology can be used many algorithms, like genetic algorithms, optimization algorithms, and DNA computing and other things. Also, I must. The last thing is OOP. I think everyone programming who knows object-oriented programming knows that the Java is now object-oriented programming language. But I think the idea of object-oriented programming, I think the inheritance idea is taken from the biology too, to make easier to use all these functions. Java and other programming languages use many functions, and when the amount of functions growing, it's like very hard to memorize all of them. For example, there was a function in C programming language, just C, not C++. There was a function A to I. Yeah. Okay. A to I, it's like abbreviation, like ASCII to integer. Then there was F to I, it's like float to integer. So there's just so many functions. But then in object-oriented programming, they took an idea from biology, I think, the classification of the living things. So they made some like integer class functions. So in Java, you can say the C function A2I is in Java written like integer dot parseInt. So it's more understandable, and the classification made these many functions more classified, more understandable. So the ideas taken from biology is sometimes associated with animal swarm algorithms. But I don't talk today about it, so let's go to the next slide. Yeah, and starting from now, I will talk about my molecular molecular computing thing, DNA computing thing. So the electronic computer, we say electronic computers and biocomputers, but there is no, I think, no biocomputers today, but some researchers say in 10 years there will be biocomputer, yeah. So electronic computers growth was told by Gordon Moore, but he told in 2005 that it can't continue forever. He meant the improvement of the processor speed doubling in each 1.5 years. So, but in the beginning, everyone was believed that it was real, but I think starting from 1985 to 2004, it was good. The law was working good, but starting from 2004, it, this graph was not so good. The speed was like not in doubling, not in 1.5 year. It's like 3.5 years and 6 years, and so on. So that means the electronic computer is reaching its technological limit. I mean, the transistor count, like millions of transistors in 1 cubic centimeters, is reaching to its limit, because if the companies like Intel, they will trying to double the density of transistors, they will face that heating problem. Like these laptops are heating very much. So if they will trying to continue this graph, then the laptops will be like I don't know, like end of that buying Cosmos rockets. So Advantages of DNA computing is like making all these molecules, DNA molecules, to do calculation for us. It's like its advantage comparing to that electronic computers, to transistors. These molecules are built before we lived. It's like it's from the biology, it's from nature, so they don't use so much energy. There is not much uh, leakage of the warmth. So, like they are working in 36 degrees Celsius, not like the electronic computer. So, low working temperature. Also, They are so many that, like in the tube, we can contain about 10 to 18th power of them. So they are working independently. So like it's like massive parallelism means almost we have not uh, four core processor, not 256 core processor. It's like 10 to 18th power core processors. So yeah, it's like comparable to only these graphical processing units. But GPUs also, like I think it's like 1024 or 2044 cores. So yeah, this is the idea. So uh, the Mr. Edelman, there was a what is that? The Mr. Edelman researcher who invented some very famous algorithms, like the security algorithm RSA, working in almost every password checking program. And so the last letter A is Edelman. So the researcher was working in many areas in biology and in computer science. So he did some experiment in 1993, and there was a paper about it in 1998 in Scientific American. And he was in his laboratory to 1 week, and he somehow could make those DNA molecules to calculate and to solve the Hamiltonian path problem. So Hamiltonian path problem is one of the very hard problems in computer science. So that is the start of the bio computing ideas. So in this research, we are using the guided combination systems. Its idea was taken from that one cell organism, infusoria. I think I believe it's called in biology. So these animals, these one cell organisms, DNA is replaced when they are mating with each other. So like the idea taken from biology is that if in personal computers working like a Turing machine and in PCs working principle in their beginning, it's like a Turing machine. That the idea principle is Turing machine, but it looks like also Turing machine. They use three types of operations like exchange, delete, insert, or something like that. So it's like a more modern approach for biocomputing compared to the first experiment of Edelman, because Edelman did it all by hand, but now it's like a more powerful machine. Yeah, so in 2000, uh, Professor Curry and Landweber said they proved that computational power of GRS is equivalent to Turing machine. So we can use it like a computer. Yeah, so also our Professor Serenono and uh, Luz from Finland, I believe, they also the paper proved in their paper proved that the sad problem it is also a competition NP hard problem. So they could solve it using GRS. It's 2007. Oh yeah. So based on that idea, we tried to solve another two NP hard problems. So uh, this is the operations we used, like insertions and deletions. These operations are used on the DNA molecules. Uh, so also we are like to prove its correctness, we use the language like this, and we are trying to solve one of the first problem is Hamiltonian path problem. The second is closest string problem. So Hamiltonian problem was solved by Edelman in 1993, but he used some manual method. But we want to use the GRS. It's a system. So if we solve Hamiltonian path problem only using electronic computer, it will be very bad working time. It's like you can see 2 and power is like exponential logarithm. So we will not, yeah, we will be able to see the end of the program. So we obtained like this asymptotic, another asymptotic value like time. It's n multiplied by m squared. So it's much lesser than this time, and yeah, you can see there is no exponential member here. Yeah, and also another problem is closest string problem. Yeah, I think many of you know what is the Hamiltonian path problem. It's like many cities and the graph is given, and you have to find the way to find the path through all the cities. Like each city is visited only once, and I think we will come back. No, not no. We should not come back to the first city. Just there must be a path which is including all the cities. And the closest string is also knows it. So there is also some exponential member, but here is not. Yeah, and this is the Hamiltonian path problem example. But yeah, since it is a NP hard problem, we can't test it on a very high number of nodes. It's just 4 nodes, and each node is also colored. Looks like, yeah, and uh, this color is used in these equations also. Like this black part of the formula is like for node number 4, and the green part, the yellow part is for the edge, yellow edge. And we start from node number 1. Yeah, and it is a very small graph, so we can see that there is a path like x1 to x3, and then x2 and x4, and this is the path the GRS system must find. Yeah, and first this s string s is like initial presentation of the graph. We should represent our graph in the form of a string, because DNA is a string. Yeah, so DNA string characters elements is like these two acids like A, T, C, G. But here, yeah, in general situation, we use many symbols. Yeah. And this is the initial representation, and we will use this algorithm to find the path. Yeah. So yeah, in every massive parallel systems, algorithms look like this. It looks like a brute force algorithm, but it works very efficiently because the molecules are many millions and billions of molecules, so they will work parallelly. Yeah. So um. mm, I shouldn't explain it in detail because it will be very long story. So first we are cutting all the vertex strings and making them like circular strings, many small circular strings, and every process is going inside some. I think it's inside some liquid uh, in a tube. So and all possible paths between n number of nodes are generated by insertion of vertex strings randomly. So uh, because there are many 10 to 18th power of molecules, we can say like all possible paths or something like randomly because they are moving randomly. So yeah, it's the idea of the algorithm is like first make all possible paths, like longer paths and shorter paths and wrong paths, correct paths, all paths were created in the form of little strings, and we will delete wrong path, like a shorter paths and longer paths, and yeah, and we in the end we will find the correct path. Yeah. So there must be like a path's length must be n. Yeah. So we first eliminate the shorter than n strings with length shorter than n and greater than n, and then we will we will check the conditions like is that path going through each city and also something yeah, if we are going through one edge repeatedly or something like that, and uh if in the end we will have this kind of string, we will have this kind of string. So we will say yes, like there is a path, but this algorithm doesn't show which uh, how looks like this path. It just it just prints out yes or no binary algorithm. So this is also the rules of the algorithm. It looks yeah, I think first look is very helpful. But yeah, the lambda is empty empty character. Yeah, and yeah, these are working. This they were numbered. Uh, each rule is responsible for each step of the algorithm. So yeah, oh, there must be some yes, no, yeah. And here we can see the result in the graphical illustration of the solution. Yeah. So initial string is here, and we can see initial string is here, but we draw another one behind him. So it means initial strings must be also some several hundred millions. Like if we are talking about DNA molecules, we can't talk about one string. It's impossible. It's like many million strings, and we will uh, cutting out these vertices, yeah, and these vertices inserted into some paths and checking if you are checking these conditions like this, for example, this in step 4 it says uh, the rule checks if this string, in this string, it starts with node x1 and ends with node xn. Yeah, so the problem statement says like if there is a path starting from first city and ending in nth city. So this is the condition. Oh, we are checking here. Oh, it's like not. It looks like not the usual mathematics. It's like a molecular expression. So yeah, sometimes it looks very awful. But yeah, and the final state is here. If we in the result, and so after several minutes, there will be string like this. Then we will say, okay, there is a path. If we can't find it, it's kind of string. So we say there is no path. So yeah, this string is very special. It's like this dollar sign is like separators. So all the separators beginning from 1 to n plus 3, they are like just one and in this order. So it means we found there is a path here. So mm, there is a theorem like saying like this algorithm will run in this time. Yeah. So the advantage, I mean, the why this is working faster than the electronical computer is like they are working parallelly. Like many units, small units working parallelly. So it means like they had many cores. It's working like a computer working with many cores. So um, and the main result, our main result was these two asymptotic times. Yeah, and we used that GRS system, which is intermolecular gene assembly. Like it's an approach assembling genes between molecules. Yeah. So there are many other HP hard problems, NP hard problems. Yeah, that was the two of problems we solved. So computational hard problems, NP hard problems can be attacked with the GRS system. But yeah, when we first uh, talked about it in Mongolia, someone asked, "Did you have $1 million?" Like because solving NP hard problem is very hard, and someone announced that if someone solves NP hard problem, he will award the researcher with $1 million, but we don't have $1 million because it's like it's a very theoretical work, theoretical paper. We didn't do anything with DNA, real DNA. It's just formulas and languages, yeah, computational languages. So it means like if in 10 years, if someone creates biocomputer based on GRS, then the person who created it can take our program and run it, and in a not exponential time, but in a not exponential time, quickly he finds the result of the HPP problem. So yeah, and yeah, and there is another thing. So yeah, this is the end of my, I think, yeah, my presentation. Thank you for your attention. Uh, and do you have any questions?
Dear participants, if you have any questions, please raise the hand. We'll be giving you permissions to speak with the professor.
Hmm? Oh, it seems we don't have any questions.
So far, no questions, sir.
Okay.
Thank you. Thank you, Professor Sudhir, for sharing your thoughts and enlightening us on bio-inspired computing. Thank you, sir.
Thank you. Thank you.
Our next session will start at 11:30 by Professor Jose from University of Santo Tomas, Philippines.
We are pleased to have Professor Jose El Senio, University of Santo Tomas, Philippines. We request you to share your keynote on the effects of overlap speech detection and speech features selection in the performance of speaker diarization with us.
Your video is visible, Professor. Your presentation is also visible, Professor.
Okay, so it's okay, huh?
Yes, Professor.
So I can proceed or?
Yes, Professor. You can proceed, Professor.
Okay. So this presentation, actually this presentation is more of a gaining, gaining some collaboration with this work, no? And of course, at the end of the day, we are looking on an app that will be helpful for not just for the research industry or research community, but also for the others, the others that could be of help on this, because I was envisioning that we could develop an app. Of course, these are some of them are already existing, wherein we can have the minutes of the meeting, okay, with a very accurate way of getting the minutes script, no? Okay. So let me the title, of course, is the effects of overlap speech detection and speech feature selection in the performance of speaker diarization. Of course, as I've said, the aim is to develop an app that could easily be used in getting the minutes of the meeting, which is almost the same as the speaker diarization, because in the minutes of the meeting, we have to identify the speakers. Okay. So this is a short presentation and direct presentation. No? We go direct to what we want. No? Okay. 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 So let me define first the speaker diarization. Okay. This is the process of partitioning the audio stream into homogeneous segments according to the speaker identity. No? So in this problem set, we are asking the question, who spoke when? Okay. So we want to know clearly who is the speaker. Okay, so that's the objective, of course, of the speaker diarization. But in this presentation, we want to improve this one by looking at the overlap detection, because definitely in a meeting or in a particular setup, there are speakers talking at the same time. No, and this problem is not so easy to solve. No, actually, the for the many papers that I have read, no, there is not much accurate. I mean, the accuracy is still low. No, so still this area is very much welcome to be explored. No? Ayan. It's not so fast. So in here, we could require this one to apply in, for example, in audio indexing. So we could have the broadcast news, as I've said before, the meeting recordings, the telephone conversation, and also to verify, of course, the speaker. Okay, and also in other pre-processing tool, wherein this could be a plug-in. No, this could be a plug-in. Okay. So the speaker diarization can enhance the readability of the automatic speech transcription by structuring the audio stream into speaker terms. And when used together with speaker recognition systems, by providing the speaker's true identity. So we have here the input of the audio of the speaker, okay, and this passed through the automatic speech recognition system, so that you can have the transcript of this audio. And definitely there are some correction, if ever, okay, because but nowadays the transcription is very good, no, because the technology is improving, so that the error is less now, no? However, still you need to have some correction, okay, so that with this correction you can now have your official record. As I've said, for example, if there is a board meeting in a company, then you can always have the minutes of the meeting with more accurate, no, with more accurate. Okay, so there is less doing the correction. Okay, and this is very important. No, this is very important. Okay. So the speaker diarization is a combination of speaker segmentation and speaker clustering. The first aims at finding the speaker change point in an audio stream, and the second aims at grouping together speech segments on the basis of these speaker characteristics. So here we have the audio, the complete audio with speaker A and speaker B. And you will notice that in between, speaker B is talking, and then suddenly speaker A butt in. No? So in that moment, there is an overlap. No? There is an overlap of this speaker A and speaker B talking at the same time. So therefore, there is a, not so clear when you do the transcription for this, no? Okay. So that when we segment them, no, you will see the speaker A in one case, and the other one with the speaker B, no? But you will notice that in speaker B, there is an overlap, no? Wherein a portion of speaker A is a part, no? So that end portion, there is an overlap, no, between speaker A and speaker B. So this is the one that we want to clarify, or to answer, no, how to deal with this, no, because definitely when you put this in a perspective, definitely the mix audio of bit A and B will give you a different result, no? Okay, that's why it's very important to do the evaluation and get the diarization error rate, no? So let's take a look on how we do this, no? So we have the miss speech, the false alarm, the speaker error over the total speech, no? So in the total speech, you do not consider the non-speech, or the one that does not come from the voice of a human or a person, no? And then you also less the overlap speech, because in this particular case, let me show you how we will handle this one, no? Para, so that you can see. Let me, because in this computation, it's very easy for us to be clear on what's the meaning of this miss-speech. So this miss-speech is you consider the speech as non-speech, even though it is a speech, no? Okay. And then for the false alarm, you assign a speaker to non-speech. So that is the vice versa naman, no? That is the vice versa of the miss-speech and the false alarm, no? And then of course the speaker error. Okay, when you assign a wrong speaker to the speech. Okay. And so of course you have to get the total speech, excluding the non-speech and the overlap speech. So why we have to remove the overlap speech? Okay, why we have to remove? Because that is our intention, no? As I've said, when we take a look on this, because it's very hard to interpret. So how will you do that, no? Whether you interpret this as an audio or as a text when you convert it to a transcript, no? But definitely you will have a hard time getting the word for this, unless speaker B has a, dominant voice out, no, such that the voice of speaker B could be converted to a transcript, no. However, with the overlap, normally you cannot get much more accuracy on doing the conversion. Okay, so what we do is we just remove this overlap, no? We just remove this overlap. That's why when we do the computation, we exclude the overlap speech. Okay, so how overlap speech affects this error rate, no? Take note that when a speaker is assigned to overlap speech, okay, the speaker error increases. Okay, so therefore with this formula, the diarization error will also increase. And in addition, no, the overlap also corrupts the speaker model, no, because take note that we have to develop a speaker model. Of course, if we have a very good input without overlap, most probably, but if we consider this overlap, then it will corrupt the speaker model. So therefore, we will have a poor speaker segmentation, which is of course one of the objective of the speaker diarization. Okay. So that's how you compute the diarization error rate. Now, let's take a look further, no, on this and scrutinize much more on how we could improve the error rate, okay, or reduce the error rate, no. And most of the time, when we could detect the overlap and remove it, okay, then we could improve it by 5 to 20%. Okay, so in other words, this is the speech of the speaker taken, and this is the speech of speaker B taken without the overlap. So in other words, we remove the overlap. Okay, the question is, will the original, no, will the original transcript be as good without the overlap? The problem is, if we include the overlap, will the original or the transcription be good also? So there is pros and cons, no? Because you will say that it's not the original because you remove the overlap. But if there is an overlap and the two audio of speaker A and speaker B are fighting each other, okay, still when you do the transcript, it will not be good also, most probably. Okay, so in our solution here, we just remove it, we discard it in our transcription. No? So therefore, when we get the speaker B, we remove that end portion. The problem, of course, when the speaker B is talking about a portion of his speech will be taken out also because of this overlap. Of course, in a meeting, we cannot say to the speakers, "Oh, do not interrupt the other speaker as the other speaker is speaking." But of course, we cannot control that. No? Okay, so it would be better that we just have to discard it. That's why we have this, no, speaker A and then speaker B, and then the discarded one. When we do the total speech, no, we remove the non-speech and the overlap speech. Okay, and in so doing, we expect that we could improve our error. Okay, or we can reduce the error by 5 to 20%. So let me give you a simple layout on this. No, so in the diarization, I put here 3 speakers, 1, 2, 3. No, and these are the time segment for each speaker. Okay, so speaker 1 is the yellow, speaker 2 is the green, and speaker 3 is the blue. Okay, so in this particular case, there are overlaps. Okay, so take note that in the ground truth, okay, there is an overlap here. Okay, and also there is an overlap here. So there are two portions wherein there are overlap of speech. No, okay. So therefore, when we count the total speech as defined in our computation, is this portion, assuming that this is the time element for that, no? Then we just make it as simpler as possible. No? So here 10 also, then here 10, okay. And then here 10, okay. Of course, this is the ground truth. This is what happened. Okay, this is what is captured by the diarization system, no? Okay, the one that is developed. Okay, and then we have here a non-speech. Okay, and then here we have the overlap. Okay, a non-speech. Okay, so that when we take a look for the miss-speech, okay, we have here as miss-speech, no? Wherein we miss. There is a speech here, but we did not assign a speaker. So miss speech. Now for the false alarm, okay, so we have 2. Okay, there is no speech here, no speech, but in the diarization, it is considered a speech. No, in other words, as a speaker is assigned, even though it's a non-speech. Also in this portion, a speaker is assigned, even though it is a non-speech. Okay, and then for the error, okay, speaker error. I mean this speaker error, yeah, definitely, because there is an overlap. Definitely, you will assign a speaker which represents these two speakers. So we consider that as an error, no? Because there is an overlap here. But since there is an error here, no? Okay, also here under the overlap, so most probably that is an error, no? And that because of that error, if we consider that in our model, okay, then it corrupts the model. Okay, so with that, we simply compute using this data and over the 110 total. Okay, so we got here the error 25.5. Okay, now with the overlap, I mean with our overlap speech detection, wherein we discard it, no, we discard it or remove it from our computation. Okay, so you will notice that when we discard it, or in other words, we detect it correctly, that it is an overlap. Okay, in this layout, we detect it for a particular speaker, but definitely since this is an overlap and we assign it to a particular speaker, then definitely it's considered an error already. No, okay. So that's why our strategy here is to remove in our computation the overlap, as long as we detect the overlap. No, so that is the most important. We need to detect the overlap. Otherwise, if we cannot detect it, then it becomes an error, because definitely there are two speakers fighting each other on that point, no, wherein we will assign a particular speaker. So it could be speaker 2 or speaker 1, no? Okay. In this particular case, okay. On the other hand, in this particular case, this is speaker 2 and speaker 3. Okay, so based on this data, you can see that removing the overlap, once the overlap is correctly detected, the error rate is reduced to 20% from 25. Okay, it is down to 20. So an improvement of 21.4%. No? Okay. So that's how we envision to use this overlap speech detection. No? Okay, but take note that this overlap speech detection is not easy to do. No? As could be seen in the past research paper, still there is so much room for improvement on this. Okay, so that's why I try to propose this objective. So to develop a novel overlap speech detection that will accurately identify the overlap speech segments in meeting type and telephone call type speech recordings. So we just limit this work to meetings and telephone calls. In telephone calls, definitely there are only two speakers. In some cases, if you have a conference, no, you can have more speakers, no. But for a meeting setup, normally more than two or more, no. For telephone call, normally it's two, but if it's a teleconference, of course, it's more than two. So, but still, the setup is still a meeting, no? Because we can apply this face to face, and definitely the telephone is online or in telephone line, no? Okay. And then the other objective is to get the right combination of speech features that will be used as input in the speaker model in order to discriminate speakers, and thereby making the speaker model to output accurate classification. So what are these speech features that we want to use? No, okay. Of course, in the ASR, this one is already perfected, no? Almost yung MFCC, ano? Okay. Now, for this work, we have to have the metrics, no? How we will evaluate our work. Okay. So we will be using accuracy, of course, the F measure, the precision, the recall, which are standard metrics, no? And then for the speaker diarization, the mentioned before, the diarization error rate, and for the speaker model, the classification accuracy. So in other words, since this involved many systems, so we have to evaluate them differently, you know? But at the end, of course, if our end up is, of course, getting the minutes of the meeting, then, of course, the correct transcript, no? Minutes, okay, the transcript of the minutes, the correct one, no? With minimal error, However, as I've said, if there is this overlap, okay, definitely some of the words will be cut out, no? So that's the problem, of course, if we will remove this overlap from our transcript, no? Okay. But definitely with the overlap, because normally when you have your meeting or when you have your telephone conversation, you do not interrupt each other. That's why you get a very good transcript. However, in some cases, if we cannot avoid it and somebody butt in, definitely there will be overlap. Okay. So let me introduce this proposed overlap speech detection. No? So we have the input, the speech recording, okay, and then we have to check the speech activity, okay, detection, okay, and then from there we have to get the overlap speech. So we diagnose, no, whether this portion has an overlap, okay. So if there is an overlap, then we have to consider that, no, yes or no, and then of course we have to do the speech segmentation and then the features extraction, okay, and then we have to take a look on the overlap speech segmentation, okay. So whether there is overlap, okay. So in other words, there is one run checking the overlap, and then another run checking again the overlap, okay. So under that we have the overlap speech clustering, okay, and then we will output the overlap speech segment. So this is the one that we will consider in the complete setup, no, in the complete setup of the meeting audio, no, or the input audio, okay. So in other words, this one will have to detect the overlap, okay, in the input, no, in the input that we have, okay. In other words, we try to look at the overlap in a particular way, you know, because if we will not concentrate on it, as I've said, the problem is not easy, you know? Okay, that's why we have to take a look. We have to have the first run and then the second run, so that we could correctly identify the overlap. Okay. Okay. Then once we have that, okay, then we also have to have this features selection setup. No. Okay. So in the features selection, speech feature selection, we observe nowadays the system is very good now. No? The accuracy is too good already. Okay, and this speech features has been selected already, and used again with high accuracy. Okay, so in this particular case, we have to consider how the output is being checked, or given out, no, whether it is accurate or not, or even though, because take note that for every speaker there are so many characteristics, no. For example, in India, in the Philippines, the way the speaker does the audio, or that's the talking, is different when it comes to diction like that, no. So that has to be considered in the speech features, whether we need to do that or we don't need at all. Okay, so we have to take a look and test so many samples, whether that is considered or not. Okay, so we will take a look on these features that has been used successfully. No? Okay. So this include, of course, number one is the MFCCs. Okay, so these are spectral in nature, and then we have the spectrogram and the prosodic, wherein this prosodic depends on a particular person, no? Because different person speak differently, so they have a different pitch, and the intensity of talking is also different. Okay, and these are affected by the formant frequencies, no? So these are prosodic, and this one is very important also when you use this one. Okay, so you can have the combination of this spectral and then the spectrogram. Okay, and the spectral and the prosodic. So in other words, you have this set, and then try to use this for each of the samples, and then we will take a look which one gives you the more accurate result, okay, and then for that, that's the one that we will apply, okay. So we have here the spectrogram and the prosodic, and then the combination of the three, spectral, spectrogram, prosodic. Of course, when we apply this one, it depends on how fast we want, no? But nowadays, because of the power of the computer, it doesn't matter anymore, no? It doesn't matter much. Okay. So how will you have to look at it, no? Because when you get a minutes, when you want to get the minutes of the meeting, of course you have to have the meeting audio, and what is best for you to get the model? Huh? How will you get the model for this? Of course, when you get a meeting and then put it in a system, so how will they know? Of course, you have to train, but you cannot train in advance because you do not know the speakers in the meeting. Who knows whether Juan, John, Philip is speaking, and what are the characteristics of that? Okay, so in other words, you have to get a slice of this meeting audio and then train. Okay, and then train. Of course, if these meetings are repeated many times and you want to use that model, then of course you have to preserve that. And when you have another meeting, then you can have another one. But if the meeting is new and the speakers are new, then you have to have something on that word. No, how will you do that? Okay, so that's a big question mark. No, how will you get the model for that? Okay, on the spot. That's what we call on the spot. And of course, many says that the best one is by, of course, by training. Yeah, training. That's the best one. No, you have to train, and to train, you need data. Okay, but the data is too small. For example, let us say, oh, you just introduce yourself, and that's just a small portion. It could not be enough. No, it could not be enough. Of course, if the meeting will be repeated many times, then you can use one of the meeting as your sample. No, but definitely in actual situation, you do not know the speaker. So that's the problem with lies. That's the problem with lies. And you have to adapt your system such that you can easily train with minimal data your system, so that you can use it in this particular case, in the speaker diarization, and in getting the meeting script or the okay. So that's another problem case, but of course that could be solved. No? That could be solved much more than getting the overlap. The overlap is much harder to solve. No, take note. That's why we concentrate on that. No? We concentrate on the overlap, because why? Because there are two speakers fighting each other out, and the model or the characteristic of speaker A or speaker B is different from each other. Okay, and when you combine the two, much more different. No? Okay. Okay, so we are now, let us say, we have already created this overlap speech detection, and then of course we have this speaker diarization. Then we can now have the speaker's diary. But in this case, as I've said, our strategy is to remove the overlap speech. No? Overlap speech. Therefore, there is some data that could not be outputted. No? Because once we remove the overlap speech, but this is minimal, because take note, in a meeting setup or in a telephone conversation setup, it's seldom that they talk at the same time. Seldom. But in any case that this happens, then you are ready to detect them. And then, as I've said, our strategy is to remove that in our output. No, in our output. Okay. So here we now have the transcription, no? As we apply the automatic speech recognition. Okay. Nowadays, this is almost perfected. No? Okay. So that's all for my presentation. As I've said, I have to direct my presentation to the meat of what we want. No? The details, of course, as engineers or as a scientist, we know these details. No? So, but what we want is the most important, especially if we can create an app that is very much helpful to the community, okay, to the researcher, to the practitioner, and of course to the industry. Okay. Good afternoon to everyone. I'm engineer Jose Arsenio. Also, I'm an assistant professor at the College of Information and Computing Sciences, University of Santo Tomas, Manila, Philippines. Thank you.
Thank you, Professor Jose El Senio, for sharing your thoughts and enlightening us.
Participants can raise a hand so that you will be given permission for asking some questions to Professor Jose. Hope there are no questions. If anybody wants to ask the question, you can write to us. We'll communicate to Professor Jose and we'll get back to you. Professor Jose, Devnath sir is in class, sir. Sir told to inform you once. After the class, he will be contacting you, Professor Jose.
Yes, yes.